We're going to extend our discussion for laminar flows with the Navier-Stokes equation to flows in pipes. Now, flows in pipes are a little bit different than flows between parallel plates, but the basic idea is still the same. It's a very simple case. Here, we're going to assume that the flow is what we call axis symmetric, which means it's symmetric around r equals 0, and that means that there's no dependence on the theta direction. We're also going to assume that it's fully developed in x, so there's no dependence on x, which means that we're only caring about u, the x direction velocity, as a function of r. That gives us a one-dimensional problem to solve. It's also very relevant to flows in pipes, various pipe flow problems. Now, we have this r direction, so it's convenient for us to use cylindrical coordinates to solve this particular problem. And then we have this sort of annular-shaped differential control volume, so we can account for the curvature or the behavior of this cylindrical geometry. So we start with the Navier-Stokes equation in polar coordinates. We're still one-dimensional for u, but now it's in r instead of in y. So we take this term and we move it over to the left-hand side and we integrate twice. And that gives us this equation here. So our boundaries for this equation, the first boundary is that when r equals 0, we have to have a finite velocity. The velocity can't go to infinity or negative infinity. So if we look at this term where we have the natural log of 0 is undefined. It's negative infinity. So in order for this to be true, C1 has to be 0, and that allows us to say that this whole term is 0. So the first boundary condition, that u has to be finite at r equals 0, gives us that C1 must be 0. The second boundary condition is the no-slip condition at the wall, where you have the velocity must be 0 at the wall. And so that gives us u equals 0 when the radius is the pipe radius. And this allows us to find C2, which we can then substitute to find the velocity as a function of r. So here we have a maximum value, which is defined by this set of terms. And then we have an additional term here. And this allows us to describe the velocity distribution inside of a round pipe.